This lecture is about regularized autoencoders. We will shortly introduce overcomplete autoencoders and then talk about different kinds of regularized autoencoders, specifically sparse autoencoders, denoising autoencoders, and constructive autoencoders. So far we have talked about autoencoders with less hidden neurons than visible neurons. These were called undercomplete. Now we talk about overcomplete autoencoders. These are autoencoders with more hidden neurons than, or more equal hidden neurons than the input neurons. So the code dimension is greater or equal than to the input dimension. We have already seen for linear autoencoders that this is the problem because we could just learn the identity mapping. And of course, this could also happen if we have more hidden than visible neurons. Like we could find a way like that we only assign a weight of 1 to these red connections and set all the other weights to 0, and then we would learn an easy identity mapping. And this, of course, would not be useful. But just having the tool to reduce the number of hidden neurons to and force the autoencoder to copy just important information might also not be the thing that we would like to have, since we would rather like to choose the hidden dimension as to adapt the capacity based on the problem. So the question is there another possibility to train such an autoencoder with larger hidden dimension and still enforce the autoencoder to not learn just the identity mapping? And one possibility is to use a regularized autoencoder in which we modify the original loss with the goal of to prevent the network from trivially copying the inputs and usually encouraging additional properties. What could these additional properties be? There are different autoencoders encouraging different properties. On the one hand is the sparse autoencoder, which learns sparse latent representations. The denoising autoencoder, which learns to be robust to noise in the image. And the contrastive autoencoder, which encourages small derivatives of the representation with respect to the input. All these regularized autoencoders can be overcomplete and non-linear, but still learn something useful about the data distribution or learn a good latent representation or a good reconstruction ability. We will now go to the different kind of regularized autoencoders in more detail. Let's first look at sparse autoencoders. As I already said, for sparse autoencoders, we would like the code or the latent representation learned to be sparse. That is, we would like that given some input, x, only a few of the hidden neurons are activated, here shown in blue, for example. So the number of active hidden neurons per training input is low. This would force the model to respond only to unique statistical features of the input data. How can we do that mathematically? We can take our standard laws that we used for training autoencoders and add to it a regularization term here. And this is, we add the L1 norm of the hidden neurons, and if we recall what we know about the properties of the L1 norm, we know that the L1 norm gauge gets larger as more entries or more hidden neurons here have an entry different from 0. So the L1 norm always searches for sparse solutions. So that's exactly what we want. And then we have the lambda for weighting the regularization term. So this would be an easy way to regularize an autoencoder. Now we look at denoising autoencoders. As the name says, denoising autoencoders should act or be able to handle noise. And this means that we would like to give the autoencoder some kind of corrupted data point or noisy data point as input. And we train it in such a way that it's able to predict the original uncorrupted or non-noisy point as in the output. That is, the representation that we learn should be robust to noise. No matter if we input the standard input or a noisy version of it, it should map to a similar representation or be able to reconstruct the same unnoisy version of the image. The procedure would be the following. We would produce such a noisy or corrupted version x tilde of x. And we could do this by randomly assigning some of the inputs to 0. So we would just switch some of the inputs off. Or we could add Gaussian noise. So draw small numbers of a Gaussian with a small variance and add this to our input. This also modifies the loss that we use. We still have a reconstruction loss, but now we would have the input to the encoder would of course be the noisy version of x, which then would be fed to the decoder. And this reconstruction of the noisy input would be compared to the original input. So the model learns to reconstruct the original input given some noisy version of the input as input to the autoencoder. So the autoencoder must learn to undo the corruption or the noising process. Formally, the corruption process introduces stochasticity to the autoencoder. We can model this with a conditional probability distribution of our corrupted data x tilde given x. And this is the distribution or sampling x tilde given x is the process of corrupting our sample x or adding noise to our sample x. Now you can recall that for feed-forward neural networks in the supervised setting, we could turn the neural network in modeling a probability distribution over outputs. In this case, probability of the label given the input x, by just modifying the output units, namely, for example, to interpret the output of the neural network as a mean of a Gaussian distribution, and training this network then with a different loss, like by maximizing the likelihood, we could train this probabilistic distribution or learn the mean of the Gaussian. And we could do the same for the autoencoder to give it a probabilistic interpretation and say that our decoder outputs the mean of a Gaussian distribution. So it outputs the mean of a distribution of x given our latent presentation z. And since training a model by maximizing the likelihood and training a model by minimizing the mean squared error is exactly the same, we could keep our mean squared error or L2 loss that we used for training an autoencoder before, or that we saw for training an autoencoder before, and this would just give a probabilistic meaning to the procedure. So we would just now interpret the output of the decoder as giving us the mean of a Gaussian and using the mean squared error, but as a equivalent to maximizing the likelihood. And then we learn probabilistic decoder. The full autoencoder then learns the probabilistic reconstruction distribution that gives us a reconstruction of our input x based on a corrupted version of the input. And for training, we just need these pairs of input points and corrupted versions of the input point. As a side note, of course, we could also make or give the encoder a probabilistic interpretation, but for now we can also, or then we would have probabilistic encoder given the probability of some latent distribution given our corrupted input, but we can also keep the encoder as a deterministic mapping. This modifies our computational graph as follows. Now we have still our input x. We use the corruption process, stochastic process, to produce our corrupted version of x, encode this via the encoder at our latent presentation set, and decode this with a decoder to get our reconstruction, which is fed to the loss function. And the loss function also gets x, our original input point, as input, because it compares the reconstruction and the original input point. So everything which is changed in the denoising autoencoder compared to the standard autoencoder is that we add this corruption process to the autoencoder. So this could, like, if you have code for a standard autoencoder, it is just adding this process of adding a corruption process, and that is changed, like maybe 1 or 2 lines of code. Now, geometrically, we can think about what this corruption and reconstruction means. And here, this black line is our data manifold, and this is the region or the manifold the data lies on. So the red points are or red crosses are given our training data. And now the corruption process is shown by this gray cycle. So this is a Gaussian added with a mean x. It's Gaussian noise with mean 0, which is centered on x. And now we add some Gaussian noise, maybe given us our disturbed or corrupted sample x tilde here. And then we learn to map these corrupted points back by learning to undo the corruption. And this is done by minimizing the difference between the reconstruction given the corrupted input point and the original input point. And as we said before, since minimizing these mean squared error is the same as maximizing the likelihood of a Gaussian distribution with mean of the reconstruction. So this is the Gauss distribution now, which gives via the decoder the mean of the Gaussian distribution, and we maximize the likelihood of these mean given our training data. This likelihood, the training data that we have is given by sampling X from our training data and sampling X tilde from the corruption process. So we just, in the code, we will just minimize the mean squared error, but this is the same as maximizing the likelihood for the training data under this probabilistic model. And for the trained model, we always map our corrupted points back to the data manifold. This is shown here by all the green lines. Like if we would have on the end of the green lines corrupted data points, they would be mapped back to the data manifold, because this difference of our reconstruction and the corrupted data points, which is just given by these green arrows, points to the data manifold, because given the corrupted data, we estimate the most probable point where the corrupted X was produced from. So this would correspond to the center of the Gaussian distribution or our corruption distribution. And since this is always placed on the data points, we learn to map back to the data manifold. These green arrows can also be interpreted as a vector field, and if we calculate such a the place where we move for arbitrary point in the space, we get such a vector field of a denoising autoencoder. Now we can go back to our small experiment. We again train Ernest, but this time with a denoising autoencoder, or we modify the system that we analyzed before in a way that we add some noise to our input points before entering or feeding them to the autoencoder. So this is a corrupted version of an MNIST data point where we added Gaussian noise. Here again we see original images and the same images with Gaussian noise. And now the autoencoder, we have used an overcomplete autoencoder with double as many hidden neurons and input neurons. And we see, we have here the original data, the corrupted data, and here the reconstruction of the autoencoder. And we see that here, even with this overcomplete setting, we don't learn a perfect reconstruction. We can easily spot these pixels like this one or here on the side, which are not exactly present in the original data. So yeah, even with more than the hidden neurons and input neurons, we don't get a simple identity mapping anymore. Now reduce the number of hidden neurons to be the same as the input neurons, and still again we have of course here also we don't have a perfect reconstruction, but a quite good one, and we can reduce it more and more and see that like a small number is still enough. The model gets a good reconstruction and is able to reduce the noise. And this is even with 32 hidden neurons is possible. But if we get few neurons, the reconstruction again gets very blurry and maybe at some point unclear which kind of digit was encoded. But this shows that the noise hinders the model to just copying even with an overcomplete architecture, and it also shows another application of autoencoders, that because we could use it if we, for example, have for some reason noisy images which could appear, for example, in medicine from a noisy measuring procedure. We could use it to reconstruct a clean image from noisy versions. The third variant of a restrictive autoencoder I want to look at is the contractive autoencoder. The goal is that for similar inputs, the learned encoding should also be very similar. That is, if we have similar input, the activation of the hidden neurons should be similar as well. Or the encoder function should not change a lot if we change the input or the output of the encoder function. If we don't want the activations to change a lot, if the input does not change a lot, this could express mathematically that we require the derivative of the hidden activations with respect to the inputs to be small. In this formula, as the hidden activations correspond to the output of the encoder, we add some regularization term to our loss function, where we have here the Frobenius norm of the encoder function, Jacobian matrix of the encoder function. And this means that we want to have the sum of all the hidden layer activations or derivatives of the hidden layer activations with respect to the inputs to be small. If the derivatives are small, this means that the function does not change a lot if we vary the input. So comparing denoising autoencoders and constructive autoencoders, we see that both are somewhat similar, but because both try to have similar performance for changes or small changes on the input data. But in the denoising autoencoder, the decoder function is trained so that it resists infinitesimal perturbations of the input, because no matter how much we put noise on our input, the decoding should be robust. And in the contractive autoencoder, we change the encoder function to resist this small perturbations. Since we try to get a close or it's the same hidden representation, a code for this varying inputs. One can wonder which of these both one should choose in practice, and both have their own advantages and disadvantages and perform well in practice. So the first advantage of a denoising autoencoder is that it's very simple to implement. We have just to add this corruption process into the code of a standard autoencoder. And we don't need to calculate something like the Jacobian matrix in the case of a contrastive autoencoder, which is more computational intensive. On the other hand, the contrastive autoencoder is deterministic, so because we just add this regularization term to the loss function, which we deterministically can calculate, so we don't have any additional stochasticity as we have by introducing the stochastic corruption process in the denoising autoencoder. This means the contrastic autoencoder, which is deterministic, might be more stable because we don't have this additional stochasticity during sampling the gradient.